Tonight, we're going to confront one of the strangest contradictions in all of physics. Everything you've ever experienced tells you the same story. When something loses energy, it slows down. A ball rolling across the floor, a car coasting to a stop, a bullet tearing through the air. Lose energy, lose speed. It's one of the most basic rules of the physical world. But light breaks this rule completely. A photon can lose an enormous amount of energy, and it will not slow down by a single meter per second. It keeps moving at exactly the same speed it always has, the same speed it always will. And when you truly understand why this happens, it doesn't just change how you think about light, it changes how you think about energy itself. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. Something so basic, so obvious, that you probably never even think about it. When something loses energy, it slows down. Roll a ball across the floor. It starts fast, spinning and sliding with whatever energy your hand gave it. But from the moment it leaves your fingers, it begins to slow. Friction is stealing its energy, converting motion into heat. Tiny amounts, imperceptible to your touch, but real. The ball keeps moving, but slower and slower. Its energy is draining away. And eventually, inevitably, it stops. All the energy it had has been transferred somewhere else. Into the floor, into the air, into the faint warmth of molecular vibrations too small to measure. And the ball is still. Zero energy. Zero speed. This isn't something you were taught in a classroom. It's something you absorbed from the world around you before you could even speak. You watched things move and stop. You threw toys and watched them land. You kicked a stone down the sidewalk and saw it tumble and roll and eventually come to rest. From the very first moments of your life, the universe was hammering a lesson into your intuition. Energy and speed are connected. More energy means more speed. Less energy means less speed. No energy means no movement at all. And this principle isn't just something that applies to balls and toys, it governs everything around you. A car on the highway is moving because its engine is converting chemical energy from gasoline into motion. Take your foot off the accelerator and the car begins to slow. Air resistance pushes against it. Friction in the tires and the drivetrain works against it. These forces are draining the car's kinetic energy, converting motion into heat and sound. Keep your foot off the gas, and the car will eventually coast to a stop. Every bit of energy the engine gave it has been transferred to the road, the air, the brakes, gone. And the car is still. A cyclist pedaling uphill is spending energy to fight gravity. Stop pedaling, and gravity immediately begins pulling you backward. You slow down, you stop. The energy you invested in climbing is gone, converted into height, and now gravity is reclaiming it. A bullet fired from a rifle has enormous kinetic energy the moment it leaves the barrel. But as it flies through the air, air resistance pushes back, slowing it, draining its energy with every meter it travels. Hit something solid, and the remaining energy transfers violently into the target. The bullet stops, its kinetic energy converted into deformation, heat, and sound. This pattern is everywhere. It is utterly universal. Or at least, it appears to be universal. Everything you have ever seen, touched, or experienced in your life confirms the same rule. Things that lose energy slow down, always, without exception. And physics backs this up with mathematical precision. There is a formula that describes this relationship exactly. For any object with mass, kinetic energy equals 1/2 times mass times velocity squared. That is the textbook equation, 1/2 mv squared. It tells you precisely how energy and speed are related for anything that has weight. Anything you can hold in your hand, anything you can put on a scale. If you know how heavy something is and how fast it's moving, you can calculate exactly how much kinetic energy it carries. And if you know the mass and the kinetic energy, you can work backward and calculate exactly how fast it must be going. Let me show you what this formula actually means with real examples. A tennis ball has a mass of about 57 grams, roughly 2 ounces. If you serve that tennis ball at 200 kilometers per hour, which is roughly the speed of a professional serve, the ball has a kinetic energy of about 88 joules. That's a modest amount of energy, enough to power a small LED bulb for several seconds. Now, take away half that energy. Maybe the ball travels through the air, slows from drag, bounces off the court surface. With half the energy gone, the ball is not traveling at 100 kilometers per hour as you might expect. It is traveling at about 141 kilometers per hour. That is because energy scales with the square of velocity, so halving the energy doesn't halve the speed. It reduces it by a factor related to the square root. But the key point is clear. The ball lost energy, and it slowed down. That is the rule. Now consider something larger. A car with a mass of about 1,500 kilograms, traveling at 100 kilometers per hour on the highway, has a kinetic energy of roughly 578,000 joules. That is a lot of energy, enough to lift that same car about 39 meters straight up into the air. If that car loses 80% of its kinetic energy to braking, its speed drops to about 45 kilometers per hour. Lose energy, lose speed. Always. A bullet from a high-powered rifle with a mass of about 10 grams, traveling at 900 meters per second, carries roughly 4,050 joules of kinetic energy. That is more energy than our tennis serve, packed into something far smaller and faster. As the bullet flies through the air, drag saps its energy, and the bullet slows. After traveling a few hundred meters, its speed might have dropped to 700 meters per second. The energy has decreased, and the speed has decreased right along with it. The relationship is absolute. For objects with mass, kinetic energy and speed are mathematically chained together. If the energy changes, the speed must change, because the mass stays the same. The ball doesn't get heavier when it slows down. The car doesn't gain mass when you apply the brakes. The bullet doesn't become more massive as it flies through the air. Mass is constant. So velocity must be the variable. Energy decreases, speed decreases, energy increases, speed increases. This is the rule. And for every object with mass that has ever existed anywhere in the universe, this rule holds without exception. But now let's turn to something that doesn't have mass at all. Light. Light is the fastest thing in the universe. It travels at about 300,000 kilometers per second through empty space. That is roughly 186,000 miles per second. In one single second, light can circle the entire planet Earth more than 7 times. In the time it takes you to blink, light has traveled roughly the distance from New York to Los Angeles and back 11 times. It's a speed so extreme that nothing in your daily experience even approaches it. The fastest commercial jet flies at about 900 kilometers per hour. Light moves more than 1 million times faster. The fastest bullet from a high-powered rifle travels at roughly 1,200 meters per second. Light is about 250,000 times faster than that. The speed of light isn't just fast, it's in an entirely different category from anything else you have ever encountered, or ever will encounter. And light carries energy. You feel this every single day. Step into sunlight and you feel warmth on your skin. That warmth is energy, delivered to your body by photons that traveled 150 million kilometers from the sun. The fact that you can see anything at all is because photons carry energy from the objects around you into your eyes, where that energy triggers chemical reactions in your retina and produces the experience of sight. Plants grow because of light energy. They absorb photons and use that energy to build sugars from carbon dioxide and water through photosynthesis. Solar panels convert light energy into electricity. Lasers use focused light to cut through metal. Light is not just illumination, it is an energy carrier, one of the most important energy carriers in the universe. So here's where the logic seems absolutely airtight. Light moves through space, light carries energy. Everything else that moves and carries energy slows down when it loses that energy. Therefore, when light loses energy, it must slow down. The logic is clean. The reasoning follows directly from everything you've experienced your entire life. Every single piece of evidence from your everyday world points to the same conclusion. And every single piece of that logic is wrong when it comes to light. Because light does not slow down when it loses energy. Not by a single meter per second. Not by a millionth of a meter per second. Not at all. A photon can lose half its energy, 90% of its energy, 99.9% of its energy, and it will continue traveling at exactly 300,000 kilometers per second through vacuum. The same speed it had before. The same speed it has always had. The same speed it always will have. Unchanged. Unwavering. Absolute. This should feel deeply wrong to you. It should feel like a violation of everything you've learned about how the world works. Because in a real sense, it is a violation. The rules you learned from everyday experience, the rules that connect energy and speed through mass, those rules apply perfectly to baseballs and bicycles and bullets. But light doesn't have mass. A photon, a single particle of light, has zero rest mass. And because it has no mass, the kinetic energy formula simply doesn't apply to it. You cannot plug zero into the mass term of 1/2 mv squared and get anything useful. The equation breaks. It was never designed to describe something without mass. For massless particles, you need a completely different equation, a different rule, and this is where things get genuinely fascinating. Because the rule that governs a photon's energy looks nothing like the kinetic energy formula. It has nothing whatsoever to do with speed. In the year 1900, a German physicist named Max Planck was struggling with a problem that had haunted physics for years. Scientists were trying to understand how hot objects radiate energy. When you heat a piece of metal, it glows. First a dull red, then a brighter orange, then yellow, then white as the temperature climbs higher. The color changes predictably with temperature. Physicists have been trying to derive a mathematical formula that would predict exactly how much radiation a hot object emits at each frequency. But every formula they came up with gave wrong answers, especially at high frequencies. Some formulas predicted that a hot object should radiate infinite energy at short wavelengths. This was obviously absurdly wrong. You can heat a poker in a fire and it doesn't obliterate the universe with infinite radiation. This spectacular failure of classical physics was called the ultraviolet catastrophe, and it was a genuine crisis. The equations were telling physicists something impossible, which meant the equations themselves were flawed at some deep level. You have to understand how alarming this was for the physicists living through it. By the end of the 19th century, classical physics felt almost complete. Newton's laws described motion. Maxwell's equations described electromagnetism. Thermodynamics described heat and energy. These frameworks have been tested and confirmed for decades, in some cases for centuries. They worked beautifully. They predicted the orbits of planets, the behavior of electric circuits, the pressure of gases. Physicists in the 1890s genuinely believed they were close to understanding everything. Some even said that all the major problems of physics had been solved, and that all that remained was filling in decimal places with more precise measurements. And then, the ultraviolet catastrophe blew a hole in the middle of everything. Here was a simple, straightforward question. How much radiation does a hot object emit at each frequency? Classical physics gave a clean, mathematical answer. And that answer was catastrophically wrong. Not slightly wrong, not off by a few percent. Infinitely wrong. The equations predicted infinite energy pouring out of every hot object in the universe at short wavelengths. A warm cup of coffee should have been emitting enough ultraviolet and gamma radiation to sterilize a room. Obviously, this was not happening. Reality and the equations had completely parted ways. This wasn't a minor discrepancy to be patched up. It was a sign that something fundamental was missing from the picture. The entire framework of classical physics, the framework that had seemed so nearly complete, was broken at a deep level that no one knew how to fix. Planck found a way out, but it required a revolutionary assumption. He proposed that energy is not continuous. It does not flow smoothly like water from a tap. Instead, energy comes in tiny, indivisible packets, which he called quanta. And each quantum of energy is determined by something very specific. Not its speed, not its mass, its frequency. The formula Planck discovered is elegant and simple. E equals h times f. Energy equals a constant, now called Planck's constant, multiplied by the frequency of the radiation. The letter h represents a tiny number, approximately 6.626 times 10 to the negative 34 joule seconds. And f represents the frequency of the light, how many times the electromagnetic wave oscillates per second. Look at this equation carefully. E equals h times f, energy on one side, frequency and a constant on the other. Speed does not appear. There is no velocity term. There is no reference to how fast the photon is traveling. The only variable that determines the photon's energy is its frequency, how rapidly the electromagnetic wave vibrates as it moves through space. That is it. A photon with a high frequency has a lot of energy. A photon with a low frequency has very little. And both of them, the high energy photon and the low energy photon, travel at exactly the same speed through vacuum. This single equation is one of the most important discoveries in the history of physics. 5 years later, in 1905, a young Albert Einstein took Planck's idea and pushed it further. Einstein argued that light itself is quantized. It doesn't just interact with matter in discrete packets, it actually exists as discrete packets. Each packet, each photon, carries a specific, fixed amount of energy determined entirely by its frequency through Planck's formula. Einstein used this insight to explain the photoelectric effect, a puzzling observation that had resisted explanation for years. When you shine light on certain metal surfaces, electrons are knocked loose, but this only works if the light has a high enough frequency. It doesn't matter how bright the light is. You can blast a metal surface with an incredibly intense beam of low-frequency red light, and not a single electron will budge. But shine a dim beam of high-frequency ultraviolet light on the same surface, and electrons start flying off immediately. Brightness didn't matter. Frequency did. Einstein explained why. Each photon either has enough energy to knock an electron free, or it doesn't. And that energy is set by frequency alone. A million low-energy photons can't pool their resources. Each one acts independently. If a single photon doesn't have enough energy, adding more photons of the same frequency won't help. This was decisive proof that the energy of light really is determined by frequency, not by intensity, and certainly not by speed. Einstein received the Nobel Prize in Physics in 1921 for this explanation. Now, let's see what this means across the full electromagnetic spectrum. Because the spectrum is the clearest possible demonstration that energy and speed are completely decoupled for light, the electromagnetic spectrum spans an astonishing range of frequencies and energies. At the lowest energy end, you have radio waves. These are the waves that carry signals to your car radio, to your television, to your Wi-Fi router, and your cell phone. Radio waves have very low frequencies, sometimes just a few thousand oscillations per second. Each radio wave photon carries so little energy that you would never feel it, never notice it. Trillions of radio wave photons pass through your body every second, and you're completely unaware of them. Move up in frequency and you get microwaves. These are the waves that heat your food in a microwave oven. They have higher frequencies than radio waves and correspondingly higher energy per photon, but still relatively modest by the standards of the spectrum. Then comes infrared radiation, which you experience as radiant heat. When you hold your hand near a hot stove and feel warmth without touching the surface, that is infrared radiation delivering energy to your skin. Each infrared photon carries more energy than a microwave photon because it has a higher frequency. Next comes the narrow band of visible light, the tiny sliver of the spectrum that your eyes happen to be sensitive to. Within visible light, the colors range from red at the low frequency end to violet at the high frequency end. Red light has a frequency of roughly 430 trillion oscillations per second. Violet light vibrates at roughly 750 trillion times per second, almost twice the frequency of red. That means each violet photon carries almost twice the energy of each red photon. And yet, red light and violet light travel through vacuum at precisely the same speed. Not approximately the same speed, exactly the same speed, 300,000 kilometers per second. A violet photon, with nearly double the energy of a red photon, does not travel a single meter per second faster. Beyond violet comes ultraviolet radiation, which is what causes sunburns. Ultraviolet photons carry enough energy to break chemical bonds in the molecules of your skin, which is why prolonged sun exposure is damaging. Then come X-rays, which carry still more energy per photon. An X-ray photon has enough energy to pass through the soft tissue of your body, which is why X-rays are used in medical imaging. And at the extreme high energy end of the spectrum are gamma rays. These are the most energetic photons in the universe. A single gamma ray photon can carry millions or even billions of times more energy than a photon of visible light. Gamma rays are produced in nuclear reactions, in the hearts of exploding stars, in matter spiraling into black holes. They are so energetic they can destroy living cells, shatter atomic nuclei, and create entirely new particles out of pure energy. And here is the fact that should stop you in your tracks. Every single one of these, from the laziest radio wave photon carrying almost no measurable energy, to the most violent gamma ray photon carrying enough energy to disrupt an atomic nucleus, travels through empty space at exactly the same speed, 300,000 kilometers per second. No exceptions. A gamma ray photon might carry 10 billion trillion times more energy than a radio wave photon, and it does not travel 1 single nanometer per second faster. The speeds are identical, perfectly, absolutely, unshakably identical. This is the fundamental difference between light and everything else you have ever experienced. For a ball or a car or a bullet, energy and speed are locked together through mass. Change the energy, and the speed must change because the mass stays constant. But for a photon, energy and speed are completely independent quantities. Energy is determined by frequency. Speed is determined by something else entirely, by the very structure of space-time itself. The speed of light is not really a fact about light, it is a fact about the universe. It is a fundamental constant woven into the fabric of reality. Any massless particle, whether it carries the energy of a faint radio whisper or the energy of a nuclear explosion, must travel at this speed. Not because of how much energy it carries, but because space-time offers no other option to something without mass. A massless particle cannot travel slower than light. It cannot speed up beyond light. It must travel at exactly the speed of light. Always. And this leads to a beautiful and profound consequence. When a photon loses energy, it does not slow down. Instead, something else changes. Its frequency drops. Its wavelength stretches. The photon shifts toward the red end of the spectrum if we're talking about visible light, or toward lower frequencies more generally if we're somewhere else on the electromagnetic spectrum. The photon is still there. It is still racing through vacuum at 300,000 kilometers per second. But it is oscillating more slowly now. It is carrying less energy in each vibration. It has become, in a very real physical sense, a different color. This is the key insight that makes everything else we're going to explore tonight make sense. For everyday objects, losing energy means slowing down. For light, losing energy means changing color. A high-energy blue photon that loses energy does not become a slow blue photon. It becomes a green photon, or a yellow photon, or a red photon. A red photon that loses more energy becomes an infrared photon. An infrared photon that loses still more energy becomes a microwave photon. Each step down in energy is a step down in frequency, a shift toward longer wavelengths. And at every single stage, through every transition, the photon is still moving at exactly the same speed it always was. Think about how deeply strange this is. Imagine if cars worked this way. Imagine you're driving a blue car at 100 kilometers per hour on the highway. You take your foot off the gas, and friction and air resistance begin draining your kinetic energy. But instead of slowing down, your car changes color. It shifts from blue to green, then from green to yellow, then yellow to orange, then orange to red. You're still moving at 100 kilometers per hour, not a fraction slower, but your car has shifted through the entire visible rainbow as it lost energy. That would be absurd for a car. It would make no sense at all. But for light, this is exactly what happens. Energy loss is not expressed as a reduction in speed. It is expressed as a reduction in frequency, as a color shift, or as a stretching of the wave. Stay with that image for a moment longer because it's important. Imagine pulling up next to another car on the highway. You ask the driver how fast they're going. They say 100 kilometers per hour. You look at their car, it's bright blue. Then you look at your car. It used to be blue, but you've been coasting for a while, losing energy to friction. Your car is now a deep red. And you look at your speedometer, 100 kilometers per hour. Exactly the same as the blue car. You have less energy. You're displaying that lower energy openly, in the color of your paint, but you have not slowed down at all. And no amount of further energy loss will slow you down. You could go from red to deep infrared, to microwave to radio wave, and your speedometer would still read 100 kilometers per hour. Exactly the same, always. This is what makes the photon so fundamentally different from every massive object in the universe. A baseball that loses energy has no choice but to slow down. A photon that loses energy has no choice but to change color. The baseball's identity, its speed, is tied to its energy. The photon's identity, its speed, is fixed by the structure of spacetime itself and has nothing to do with how much energy it carries. The baseball wears its energy in its motion. The photon wears its energy in its frequency. And that distinction, that decoupling of energy from speed, is the entire reason we are here tonight. And this raises the question that the rest of our journey tonight is going to answer. If losing energy doesn't slow light down, what actually causes a photon to change its frequency? What makes light shift toward the red? What physical processes in the real universe can drain energy from a photon or change the energy an observer measures while leaving its speed completely untouched? There are several answers, and each one reveals something different and surprising about how the universe operates. Some involve genuine physical interactions where energy flows from the photon into matter. Others are stranger, cases where the photon hasn't really changed at all, but different observers simply measure different frequencies depending on how they are moving or where they're sitting in a gravitational field. And at least one involves the universe itself, the expansion of space-stretching photons as they travel across billions of light years of cosmic distance. Each of these mechanisms tells a different story about the relationship between light and energy, and each one reinforces the same astonishing fact. A photon can gain energy, lose energy, or be measured with a completely different energy by a different observer. And through all of it, through every interaction and every shift, it never changes speed. Not by a single meter per second. Because for light, energy was never about speed in the first place. Now, imagine you're standing on a sidewalk, a quiet street, nothing happening. And then you hear it, far away at first. An ambulance, approaching. The siren is high-pitched, urgent, that sharp, wailing tone cutting through the air. The ambulance gets closer, closer. The siren gets louder, but also, and this is the part people don't always notice, the pitch stays high, maybe even seems to climb slightly as the vehicle rushes toward you. And then, the ambulance passes. It flies by in a blur of flashing lights, and in that instant, something changes. The pitch of the siren drops, noticeably, clearly. What was a high, sharp wail is now a lower, deeper tone, pulling away from you down the road. The ambulance hasn't changed its siren. The paramedic inside didn't reach over and turn a dial. The siren itself is producing the exact same tone it was producing 5 seconds ago. But the sound reaching your ears is different now, lower in pitch, longer in wavelength, less energy arriving at your eardrums each second. You have just experienced the Doppler effect. And this effect, Discovered by an Austrian physicist named Christian Doppler in 1842, is going to be our entry point into one of the most important ideas in all of astronomy. Because the exact same thing happens to light. Here's what is actually going on with that ambulance siren. Sound is a wave. It travels through the air as a series of compressions and expansions, regions where air molecules are squeezed together, followed by regions where they are spread apart. The frequency of a sound wave, how many compressions reach your ear each second, determines its pitch. High frequency means high pitch. Low frequency means low pitch. When the ambulance is approaching you, each successive compression is emitted a little closer to you than the one before. The ambulances move toward you in the time between emitting one compression and the next. So the compressions arrive at your ear more frequently. They're bunched together. The frequency you measure is higher than the frequency the siren is actually producing. And higher frequency means higher pitch. That's why the approaching siren sounds higher than it really is. When the ambulance passes and starts moving away, the opposite happens. Each successive compression is emitted a little farther from you than the one before. The ambulance is moving away, stretching the gap between each compression by the time it reaches your ear. The compressions arrive less frequently. The frequency you measure is lower than the frequency the siren is actually producing. Lower frequency means lower pitch. That's why the receding siren sounds deeper. Now here is the crucial thing to notice. The siren hasn't changed. It is producing the exact same tone at the exact same frequency the entire time. What changed is the frequency that reaches your ears, because the motion of the source has compressed or stretched the waves. The Doppler effect is not about the source changing. It is about the observer measuring something different because of relative motion between the source and the observer. And this is exactly what happens with light. Light is an electromagnetic wave. It has a frequency and a wavelength, just like sound. But instead of air molecules compressing and expanding, light consists of oscillating electric and magnetic fields propagating through space. And just like sound waves, light waves can be compressed or stretched by relative motion between the source and the observer. When a light source is moving toward you, the light waves get compressed. The wavelengths get shorter. The frequency gets higher. And as we learned, higher frequency means higher energy per photon. The light shifts toward the blue end of the visible spectrum, which is why astronomers call this blue shift. The photons arriving at your eyes or your telescope carry more energy than the photons the source actually emitted, as measured in the source's own reference frame. When a light source is moving away from you, the light waves get stretched. The wavelengths get longer. The frequency gets lower. Lower frequency means lower energy per photon. The light shifts toward the red end of the spectrum. This is called redshift. The photons arriving at your detector carry less energy than the photons the source emitted. And this is where it gets deeply, profoundly strange. Because with the ambulance, you can wave this off as just an interesting acoustic effect. Sound waves bunching up, sound waves spreading out, fine. But with light, we are talking about energy. Real, measurable, physical energy. A blue shifted photon genuinely carries more energy than the source emitted. A red shifted photon genuinely carries less. The energy you measure is different depending on whether the source is approaching or receding. And this leads to an uncomfortable question. Where did the extra energy come from in the case of blue shift? And where did the missing energy go in the case of redshift? The answer is going to feel unsatisfying at first, but stay with it because it reveals something fundamental about how the universe works. The answer is nowhere. The energy didn't come from anywhere, and it didn't go anywhere. There is no missing energy and no extra energy. The photon itself has not changed. Nothing happened to it during its journey through space. It was not accelerated. It was not decelerated. It did not collide with anything, interact with anything, or exchange energy with anything. It is the exact same photon it was when it left the source. What changed is the observer. The observer is in a different state of motion than the source, and because of that different state of motion, the observer measures a different frequency for the same photon. Different frequency means different energy. But this isn't energy appearing from nothing or disappearing into nothing. It is a reflection of the fact that energy, in the physics of relativity, is not an absolute quantity. It depends on your frame of reference. Different observers moving at different speeds will measure different energies for the same photon, and all of them are correct. None of them is wrong. None of them is more real than the others. Energy is relative. Not relative in the casual everyday sense of the word. Relative in the precise physical Einsteinian sense. It depends on who is doing the measuring and how they are moving. Think about what this means. You and a friend are standing in a field. A distant star is emitting photons. You are standing still relative to the star. So you measure the photons at their emitted frequency. Your friend is jogging toward the star at some speed. Your friend measures the same photons at a slightly higher frequency, slightly bluer, slightly more energetic. You both measured the same photons at the same moment. You got different numbers. Neither of you is wrong. There is no correct energy for those photons independent of who is measuring them. This is a deeply counterintuitive idea. We are used to thinking of energy as something concrete, something objective, something that exists in a definite amount regardless of who is looking. A battery has a certain amount of energy stored in it. A gallon of gasoline contains a certain number of joules. These seem like absolute facts about the world, not things that change depending on your perspective. And for everyday objects at everyday speeds, this intuition works fine. The differences in energy measured by observers moving at ordinary speeds are so tiny they are completely unmeasurable. But for light, and for objects moving at significant fractions of the speed of light, the differences become enormous. A photon from a distant galaxy racing away from us at a substantial fraction of light speed can arrive at our telescopes with half the frequency it was emitted with, meaning half the energy. And a photon from a source rushing toward us can arrive with double the frequency, double the energy. These are not small corrections. These are dramatic, measurable changes. And they are entirely a consequence of relative motion, not of anything happening to the photon itself. Let me give you a concrete example. Hydrogen is the most common element in the universe. When hydrogen atoms get excited, they emit light at very specific, well-known frequencies. One of the most important is a frequency called H-alpha, which produces a distinctive red glow with a wavelength of about 656 nanometers. This wavelength has been measured in countless laboratory experiments on Earth. We know it with extraordinary precision. It is one of the best known quantities in all of spectroscopy. Now, when astronomers point a telescope at a distant star and spread its light into a spectrum, they look for this H-alpha line. If the star is not moving relative to Earth, the line appears at exactly 656 nanometers. right where it should be. But if the star is moving away from Earth, the line appears at a longer wavelength, maybe 660 nanometers instead of 656. It has shifted toward the red. The star is receding. If the star is moving toward Earth, the line appears at a shorter wavelength, maybe 652 nanometers. It has shifted toward the blue. The star is approaching. The amount of the shift tells you exactly how fast the star is moving toward or away from you. A bigger shift means a faster speed. This is one of the most powerful tools in all of astronomy. Without ever leaving Earth, without ever visiting a star, you can measure how fast that star is moving along your line of sight just by looking at the color of its light. This technique was used in the early 20th century to make one of the most important discoveries in the history of science. In 1912, an American astronomer named Vesto Slipher, working at the Lowell Observatory in Arizona, began carefully measuring the spectra of what were then called spiral nebulae. These fuzzy spiral shapes in the sky had been observed for decades, but no one knew what they were. Some astronomers thought they were clouds of gas within our own Milky Way. Others suspected they might be entire galaxies far beyond the Milky Way, each containing billions of stars. Slipher started measuring the Doppler shifts of these spiral nebulae, and what he found was remarkable. Almost all of them were redshifted. Their spectral lines were shifted toward longer wavelengths, toward the red. This meant almost all of them were moving away from us, and not just moving away slowly. Some of them were receding at speeds of hundreds or even thousands of kilometers per second. At the time, no one quite knew what to make of this. Why would nearly everything in the sky be flying away from us? It seemed bizarre. It took another decade and a half before the implications became clear. In 1929, Edwin Hubble, working with much better distance measurements, showed that the redshift of these objects was proportional to their distance. Objects twice as far away were moving away twice as fast. Objects 10 times farther were moving 10 times faster. This relationship, now called Hubble's law, was the first direct evidence that the universe is expanding. And it was discovered through the Doppler shift of light. Think about what that means in the context of our discussion tonight. Every distant galaxy is redshifted. The light from those galaxies arrives at our telescopes with lower frequency and lower energy than it had when it was emitted. By the classical intuition you've had your whole life, you'd expect this to mean the light slowed down during its journey. It lost energy, so it must have slowed down. But it didn't slow down. It arrived at exactly 300,000 kilometers per second, the same speed it was traveling when it left the galaxy billions of years ago. Its energy is lower, but its speed is unchanged. The energy decrease is entirely accounted for by the decrease in frequency. Now, I want to take a moment here to be very precise about something because it matters. The Doppler redshift we've been discussing so far is specifically the redshift caused by the motion of the source relative to the observer through space. This is sometimes called the kinematic Doppler effect, or the special relativistic Doppler effect. It arises because the source and the observer are in different states of motion. It is a real, measurable, physically important phenomenon, but it is also, in a fundamental sense, a matter of perspective. The photon hasn't been altered. No energy has been deposited anywhere. No physical process has acted on the photon during its flight. Different observers, moving at different speeds, simply assign different frequencies and therefore different energies to the same photon. This is worth sitting with for a moment, because it tells us something profound about the nature of energy itself. In our everyday experience, energy feels like a thing, a substance, something you can pour from one container to another, like water. You fill a tank with gasoline, and the energy is in the tank. You burn the gasoline, and the energy moves into the engine. Energy feels real, tangible, countable, and it is real, but it is not absolute. The amount of energy you measure depends on your frame of reference. A baseball sitting on a table has zero kinetic energy from your perspective. But from the perspective of someone flying overhead in a jet, that baseball is moving at 900 kilometers per hour, and it has a tremendous amount of kinetic energy. Which answer is correct? Both. Both are correct. Energy is frame dependent, even for ordinary objects. For everyday objects, this frame dependence is usually unimportant. We all agree on a common frame of reference, the surface of the Earth, and we measure everything relative to that. The ball on the table has zero kinetic energy because it's not moving relative to us and relative to the Earth. We don't usually worry about how much kinetic energy it has from the perspective of a passing jet or a distant star. But for light, you can't get away with ignoring this. Light doesn't have a rest frame. A photon is always moving at 300,000 kilometers per second in every reference frame. You can't stand next to a photon and measure its energy at rest, because a photon is never at rest. Every measurement of a photon's energy is made by an observer in some particular state of motion, and different states of motion give different answers. This means that when we ask how much energy does this photon have, we are really asking how much energy does this photon have as measured by this particular observer in this particular state of motion. The question doesn't have a single universal answer. It has many answers, one for each possible observer, and all of them are equally valid. Let me give you another example to drive this home. Imagine two astronomers. One is on Earth, the other is on a spacecraft traveling towards a distant star at 10% of the speed of light. Both astronomers observe the same star, both measure the star's light. The astronomer on the spacecraft, who is rushing toward the star, measures the light with a higher frequency and higher energy. The astronomer on Earth, who is essentially stationary relative to the star, measures the light with a lower frequency and lower energy. The difference can be calculated precisely using the relativistic Doppler formula. And here is the key. Both astronomers are right. The photons haven't changed. The star hasn't changed. But the two observers, because they are in different states of motion, assign different energies to the exact same light. Neither measurement is more real or more correct than the other. This might feel like a technicality, a philosophical detail with no practical consequences. But it has enormous consequences for astronomy and for our understanding of the universe. The Doppler redshift of distant galaxies is the foundation of modern cosmology. It's how we discovered the expansion of the universe. It's how we measure the distances to far-off galaxies. It's how we determine the velocities of stars orbiting the center of our galaxy, how we detect the wobble of stars being tugged by orbiting planets, and how we measure the speeds of binary stars orbiting each other. Every time an astronomer reports a velocity measured through redshift, they are using the Doppler effect. And every single one of those measurements confirms the same principle. Light changes frequency depending on relative motion. It does not change speed. The Doppler effect also works in reverse. When a source moves toward an observer, the light is blue shifted. Its frequency increases, its wavelength decreases, its energy per photon goes up. And again, the speed is unchanged. The photon arrives at 300,000 kilometers per second, whether it's blue shifted, red shifted, or perfectly unchanged. This is important because it means the effect is symmetric. Light can appear to gain energy or lose energy depending entirely on the direction of relative motion. Move toward the source and you see blue shift. Move away and you see red shift. The photon doesn't care which direction you're going. It doesn't adjust itself. It just arrives, and you measure whatever frequency your state of motion produces. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, is one of the very few galaxies that is blue shifted, while nearly every other galaxy in the observable universe is red shifted. Receding from us as the universe expands, Andromeda is approaching the Milky Way at roughly 110 kilometers per second. Its light is compressed by this approach. The spectral lines of hydrogen and other elements in Andromeda appear at slightly shorter wavelengths than they would if Andromeda were stationary relative to us. Each photon from Andromeda arrives with a slightly higher frequency and a slightly higher energy than it was emitted with, as measured in our frame. And once again, those photons arrive at exactly the same speed as every other photon in the universe. The blue shift gives them more energy, not more speed. There is something deeply beautiful about this. The Doppler effect for light reveals that the universe is in motion. Stars are moving, galaxies are moving, clusters of galaxies are moving. Nothing is sitting perfectly still, and we can detect all of this motion without going anywhere, without traveling a single mile from Earth, just by carefully measuring the frequencies of light. The universe is telling us how it moves through the colors of its light. Redshift whispers that something is retreating. Blue shift announces that something is approaching, and the speed of the light carrying those messages never changes. Consider how this applies to something closer to home. Our own sun is orbiting the center of the Milky Way at about 230 kilometers per second. As it moves, stars on one side of its orbit are approached by the sun, and their light is very slightly blue shifted from our perspective. Stars on the other side are receded from, and their light is very slightly red shifted. By measuring these tiny shifts across thousands of stars, astronomers can map the rotation of our galaxy. They can determine how fast the Milky Way is spinning at different distances from the galactic center. And these measurements revealed something astonishing. The outer regions of the galaxy rotate faster than they should, if only the visible matter were providing gravity. Something else, something invisible, is adding extra gravitational pull. This was one of the earliest lines of evidence for dark matter, the mysterious substance that makes up about 27% of the universe's total energy content. And it was discovered through the Doppler shift of starlight, through light changing frequency without changing speed. The Doppler effect for light also plays a role in detecting planets around other stars. When a planet orbits a star, it doesn't just go around the star, it also pulls the star very slightly in a tiny orbit of its own. The star wobbles. When the star wobbles toward us, its light is slightly blue shifted. When it wobbles away, its light is slightly red shifted. These shifts are minuscule, sometimes corresponding to speed changes of just a few meters per second, but modern spectrographs are precise enough to detect them. More than 1,000 exoplanets have been discovered using this radial velocity method, all based on the Doppler shift of starlight. Let me bring this back to our central question. How does light lose energy without slowing down? The Doppler redshift gives us our first answer, and it is a strange one. In the case of Doppler redshift, light hasn't actually lost energy at all. Nothing happened to the photon. No energy was transferred, no interaction took place, no force acted on it. The photon is identical to what it was when it was emitted. What changed is the observer's frame of reference. A different observer in a different state of motion would measure a different frequency and a different energy for the same photon, and all observers would measure the same speed. This is perhaps the single most important lesson of the Doppler redshift. Energy is not absolute. It is observer dependent. A photon does not carry a fixed amount of energy stamped on it like a price tag. It carries a frequency, and different observers in different states of motion will measure that frequency differently. Higher if approaching, lower if receding. And different frequencies mean different energies, because E equals h times f. But the speed is the one thing everyone agrees on. Every observer, regardless of their motion, measures the photon traveling at 300,000 kilometers per second through vacuum. Speed is absolute. Energy is relative. This is the exact opposite of what your daily experience would lead you to expect. For a baseball, energy and speed are tightly coupled. Change the energy, and the speed changes. But everyone basically agrees on the speed of a baseball. If it's going 90 miles per hour, it's going 90 miles per hour. The speed feels absolute, and the energy is calculated from it. For a photon, speed is genuinely absolute, locked at 300,000 kilometers per second for all observers. But energy is relative, changing from observer to observer depending on their motion. The roles are reversed. What was absolute for matter becomes relative for light. What was relative for matter becomes absolute for light. This reversal is not a quirk or an accident. It is built into the deepest structure of physics. It follows directly from the principle that the speed of light is the same for all observers, one of the foundational postulates of Einstein's special relativity. And it has been confirmed by over a century of experiments, observations, and practical applications. So, the next time someone asks you whether light slows down when it loses energy, you can give them the first piece of the answer. In the case of Doppler redshift, the light hasn't even lost energy in any absolute sense. It has the same frequency it always had from the source's perspective. A different observer simply measures a different frequency because of relative motion. The energy appears to change, but only because energy depends on who is measuring it. And the speed never changes. Not by a fraction of a meter per second. Not ever. But the Doppler effect is only part of the story. There are situations where something more physical happens. Situations where the photon genuinely interacts with matter and loses energy in a way that every observer agrees on. And there are situations where the very geometry of spacetime itself changes the frequency of a photon, not because of relative motion, but because of gravity. These are different phenomena with different explanations. And they are where we are going next. So far, we have explored one way that light can appear to lose energy without slowing down. The Doppler redshift showed us that the energy of a photon depends on who is measuring it. A source moving away from you emits photons at one frequency, and you receive them at a lower frequency because your relative motion stretches the wavelengths. The photon itself hasn't changed. Nothing acted on it. The difference is entirely about perspective, about the frame of reference of the observer. But now we are going to enter territory where something more profound is happening. We are going to talk about gravity, and gravity does something to light that goes beyond perspective. It changes what different observers experience in a way that is rooted not in motion through space, but in the very fabric of space-time itself. Let's begin with an experiment. A thought experiment, the kind Einstein loved. Imagine you're standing on the surface of a massive planet, a very dense, very heavy world. You have a flashlight and you point it straight up toward the sky and turn it on. A beam of photons races upward, climbing away from the planet's surface, heading toward the stars. Now, imagine your friend is far above you, orbiting the planet in a spacecraft, well beyond the reach of the planet's strongest gravitational pull. Your friend has a detector, and she catches some of the photons from your flashlight. She measures their frequency, and what she finds is that the frequency she measures is lower than the frequency you emitted. The light has been redshifted, not because you are moving away from her. You might be perfectly stationary relative to her, not because the photon interacted with anything during its climb. There is nothing between you and your friend but empty vacuum. The photon traveled through nothing, it hit nothing, it bounced off nothing, and yet its frequency is lower when it arrives. Its energy, as measured by your friend, is less than the energy you put into it with your flashlight. This is gravitational redshift, and it is one of the strangest predictions of Albert Einstein's general theory of relativity, published in 1915. Einstein didn't just predict that massive objects bend the path of light, which they do. He predicted that gravity affects the frequency of light itself, and he was right. But here is what you must be very careful about. It is tempting, almost irresistible, to explain gravitational redshift by saying that the photon is climbing out of a gravitational well and losing energy in the process, like a ball thrown upward, which slows as gravity pulls it back. The ball loses kinetic energy as it gains height. So maybe the photon loses energy the same way. Maybe gravity is dragging on the photon, pulling it back, sapping its energy as it struggles to escape. This picture is intuitive. It feels natural, but it is wrong, or at least it is deeply misleading. Gravity is not pulling on the photon in the way it pulls on a ball. The photon is not slowing down. It is not decelerating. It does not feel a force in the classical sense. The photon passes through the gravitational field at exactly the speed of light. The same speed it always travels. It does not labor upward. It does not struggle. It does not lose velocity. The speed of light is not negotiable, not even for gravity. So what is actually happening? The answer requires a shift in how you think about gravity itself. In Einstein's general relativity, gravity is not a force in the traditional sense. It is a consequence of the curvature of space-time. Massive objects like planets and stars warp the fabric of space-time around them. They create a kind of curvature, a bending, a distortion in the geometry of space and time. And one of the most important effects of this curvature is that it affects the flow of time. This is not a metaphor. Time literally passes at different rates depending on where you are in a gravitational field. Near the surface of a massive object, deep in the gravitational well, time passes more slowly than it does far away from the object. This is called gravitational time dilation, and it has been measured directly in experiments. It is not theoretical. It is not speculative. It is observed fact. Here is how this connects to light. When you emit a photon from the surface of a massive planet, you're emitting it from a region where time runs slowly. You measure the photon's frequency using your local clock. You count how many oscillations occur per second on your clock, and you assign the photon a frequency based on that count. Now, your friend in orbit far above is in a region where time runs faster. Her clocks tick more quickly than yours. When she receives the photon and counts how many oscillations arrive per second on her clock, she gets a smaller number. Not because the photon has changed, but because your seconds are longer than hers. Your clock runs slowly, letting more oscillations accumulate per second. Her faster clock lets fewer oscillations arrive per second. The same photon, oscillating at the same fundamental rate, appears to oscillate fewer times per her second than it did per your second. The result is that she measures a lower frequency. Lower frequency means lower energy because E equals h times f. The photon has been gravitationally redshifted. But the redshift didn't happen because something acted on the photon during its flight. It happened because the photon was emitted in a region of slow time and received in a region of fast time. The difference in clock rates between the two locations is what produces the frequency shift. The photon is the messenger. The message it carries, its frequency, is interpreted differently at the two ends because the clocks at the two ends tick at different rates. Think about how strange this is. You and your friend are both looking at the same photon. You measured it at a high frequency. She measured it at a low frequency. Neither of you is wrong. Both measurements are physically correct. The photon doesn't have a single true frequency independent of the gravitational environment in which you measure it. Frequency, and therefore energy, depends on where you are in the gravitational field. Just as the Doppler effect showed us that energy depends on your state of motion, gravitational redshift shows us that energy depends on your position in a gravitational field. Einstein first predicted this effect in 1907, 8 years before he completed general relativity. He refined the prediction in 1911, but it took decades before technology was precise enough to test it directly in a laboratory setting. The breakthrough came in 1959 when two physicists at Harvard University, Robert Pound and Glenn Rebka, performed one of the most elegant experiments in the history of physics. The Pound-Rebka experiment was beautifully simple in concept. They set up a source of gamma-ray photons in the basement of the Jefferson Tower at Harvard and a detector at the top of the tower, about 22.5 meters above. The photons traveled upward from the basement to the rooftop. That is a tiny distance by astronomical standards. The difference in gravitational potential between the basement and the rooftop is minuscule compared to the difference between, say, the surface of a neutron star and deep space. But Pound and Rebka were using gamma-ray photons, which have very high frequencies, and they had an incredibly precise technique for measuring tiny frequency shifts, a technique based on a phenomenon called the Mossbauer effect, which allows you to measure frequency changes with extraordinary accuracy. What they found was exactly what Einstein had predicted. The gamma-ray photons arriving at the top of the tower had a slightly lower frequency than the photons emitted at the bottom. The shift was minuscule, roughly 2 parts in 1,000 trillion, but it was there. It was measurable, and it matched Einstein's prediction to within 10%. Later refinements of the experiment brought the agreement to within 1%. Gravity had shifted the frequency of the photons, not by acting on them as a force during their flight, but by the simple fact that time runs at different rates, at different heights, in a gravitational field. This result has practical consequences that affect your daily life, even if you don't realize it. GPS satellites, the satellites that let your phone know where you are, orbit Earth at an altitude of about 20,000 kilometers. At that altitude, the gravitational pull from Earth is weaker than at the surface. According to general relativity, time runs slightly faster up there than it does down here. The difference is tiny, roughly 45 microseconds per day faster. That might sound insignificant. 45 microseconds is 45 millionths of a second. You wouldn't notice that in a lifetime of normal activity, but GPS works by measuring the travel time of radio signals with extraordinary precision. Light travels about 300 meters in 1 microsecond. So an error of 45 microseconds corresponds to a distance error of about 13.5 kilometers. If GPS satellites did not correct for gravitational time dilation, your position reading would drift by more than 13 kilometers per day. Within a single week, GPS would be so inaccurate that it would be completely useless for navigation. Your phone would tell you that you are standing in the middle of a lake when you are actually in a parking lot 3 towns over. The fact that GPS works, the fact that it puts you on the correct street in the correct city, is direct physical proof that gravitational time dilation is real. Every time you open a map on your phone and see a little blue dot showing your location, you are seeing experimental confirmation of Einstein's general theory of relativity. The engineers who designed GPS had to include relativistic corrections in the satellite software. Without those corrections, the system would fail within hours. Gravitational redshift also applies in much more extreme environments. Near the surface of a neutron star, where gravity is billions of times stronger than on Earth, a photon emitted from the surface can lose a significant fraction of its energy by the time it reaches a distant observer. A photon that started as an X-ray might arrive as ultraviolet light or even visible light. Its frequency dramatically reduced by the intense gravitational field. And near the event horizon of a black hole, gravitational redshift becomes extreme. A photon emitted just outside the event horizon and heading outward is redshifted enormously. As the emission point gets closer and closer to the event horizon, the redshift grows without limit. A photon emitted right at the event horizon would be infinitely redshifted, its frequency driven to zero, its energy drained completely, at least as measured by a distant observer. This is one way of understanding why nothing can escape from a black hole. Any photon trying to leave from the event horizon has its frequency redshifted to zero. It loses all its energy, not through some mechanical process, but because the curvature of space-time at the event horizon is so extreme that time essentially stops relative to an outside observer. And through all of this, the photon never slows down, not near the neutron star, not near the black hole, not anywhere. Its local speed, the speed measured by any observer it passes, is always 300,000 kilometers per second. The gravitational field changes its frequency. It changes its measured energy, but it cannot change its speed. Because speed and energy are decoupled for photons. They are governed by completely different aspects of physics. Speed is set by space-time itself. Energy is set by frequency. And frequency is affected by the curvature of space-time in ways that speed is not. Now let's turn to something very different. Something much more straightforward in one sense, but no less important. We are going to talk about what happens when a photon actually hits something, when it collides with matter and physically transfers energy in a way that every observer, regardless of their frame of reference or gravitational position, would agree on. This process is called Compton scattering, and unlike the Doppler effect or gravitational redshift, Compton scattering involves a genuine physical interaction. The photon doesn't just appear to have different energy depending on who is looking. It actually gives up some of its energy to another particle. There is a real transfer, a real exchange. Energy leaves the photon and goes into something else, and you can point to where it went. The effect was discovered in 1923 by an American physicist named Arthur Compton. He was doing experiments with X-ray photons, firing them at targets made of lightweight atoms. When the X-ray photons hit the electrons in those atoms, something interesting happened. The photons that bounced off, that scattered away from the target, had a lower frequency than the photons that went in. They were redshifted. And the amount of redshift depended on the angle at which the photon scattered. Photons that bounced straight back had the largest frequency shift. Photons that barely deflected, just grazing the electron, had almost no shift at all. This was a puzzle for classical physics. If light were just a wave, like ripples on a pond, you wouldn't expect its frequency to change when it bounced off an electron. Waves reflect off surfaces all the time without changing frequency. You shout at a wall, and the echo comes back at the same pitch. But Compton's X-rays were coming back at a different frequency. Lower frequency. Less energy. Something was absorbing part of the photon's energy during the collision. The explanation came from treating light as particles, as photons, each carrying a specific amount of energy determined by E equals h times f. When a photon collides with an electron, the collision is like a billiard ball hitting another billiard ball. The photon transfers some of its energy and momentum to the electron. The electron recoils, flying off with kinetic energy that it didn't have before the collision. And the photon continues on its way, but now with less energy than it started with. Less energy means lower frequency. Lower frequency means longer wavelength. The photon has been redshifted by the collision. The mathematics of Compton scattering are precise and testable. Compton worked out the exact relationship between the incoming photon's wavelength, the outgoing photon's wavelength, and the angle at which the photon scattered. The formula depends on the mass of the electron and on Planck's constant, and it makes predictions that can be checked in the laboratory. And those predictions match experimental results perfectly, every single time. Compton received the Nobel Prize in Physics for this work because it provided some of the most compelling evidence that light really does behave as particles, as photons, carrying discrete amounts of energy and momentum. What makes Compton scattering fundamentally different from the Doppler effect and gravitational redshift is that here the energy genuinely goes somewhere. In Doppler redshift, no energy was transferred. Different observers simply measured different frequencies. In gravitational redshift, the difference arose from the geometry of spacetime and the different rates at which clocks tick at different gravitational potentials. But in Compton scattering, there is a real physical collision. The photon hits an electron. The electron gains kinetic energy. The photon loses an equal amount of energy. Energy is conserved in the straightforward, familiar sense. Everything adds up. You can measure the energy of the incoming photon, measure the energy of the outgoing photon, measure the kinetic energy of the recoiling electron, and confirm that the total is the same before and after. This is the kind of energy loss that makes intuitive sense. Something interacted with the photon. Energy was transferred. The books balance. There is no mystery about where the energy went. It went into the electron. You can see the electron recoil. You can measure its speed. You can calculate its kinetic energy. It all checks out. And yet, even here, the photon does not slow down. After the collision, the photon continues traveling at exactly 300,000 kilometers per second. Its energy is lower, its frequency is lower, its wavelength is longer, but its speed is unchanged. It lost energy and it didn't slow down. It changed color, it shifted toward the red. But it kept moving at the speed of light because that is what photons do. That is all photons can do. This is worth pausing on because it illustrates the central theme of everything we've been exploring. For a billiard ball, if it hits another billiard ball and transfers energy, the first ball slows down. That is obvious. That is what always happens. But for a photon, hitting an electron and transferring energy does not cause the photon to slow down. It causes the photon to change frequency. Energy leaves, frequency drops, speed stays the same. The rules for massless particles are simply different from the rules for massive ones. Compton scattering is not a rare or exotic phenomenon. It happens everywhere in the universe, constantly. When X-rays from a distant astronomical source pass through clouds of hot gas, some of those X-ray photons scatter off electrons in the gas. Each scattering event can shift the photon's frequency, changing its energy. In the hot gas surrounding galaxy clusters, photons from the cosmic microwave background, the faint radiation left over from the Big Bang, scatter off the energetic electrons in the gas and actually gain energy. The electrons are so hot, moving so fast, that they transfer energy to the photons rather than the other way around. The photons emerge with a higher frequency, blue shifted by the interaction. This process, called the inverse Compton effect, is the same physics running in the opposite direction. In medical imaging, Compton scattering is one of the main ways X-ray photons interact with the tissues of your body. When you get an X-ray at the hospital, some of the photons pass straight through you and hit the detector on the other side, forming the image, but others scatter off electrons in your body, changing direction and losing energy. These scattered photons can create noise in the image, which is why X-ray technicians use various techniques to minimize the effect of scattered photons on image quality. In radiation therapy for cancer treatment, Compton scattering is the dominant interaction mechanism for the high-energy photons used to destroy tumor cells. The photons transfer energy to electrons in the tumor tissue, and those energetic electrons go on to damage the DNA of cancer cells, preventing them from dividing. Understanding Compton scattering precisely is essential for calculating radiation doses and ensuring that the treatment is effective while minimizing damage to healthy tissue. So Compton scattering is not some abstract theoretical curiosity. It is happening around you and inside you and throughout the universe all the time. It is a fundamental way that photons interact with matter, and every single instance of it confirms the same rule. The photon transfers energy to the electron. The photon's frequency decreases. The photon's speed stays exactly the same. Now let's step back and compare the three mechanisms we've explored: Doppler redshift, gravitational redshift, and Compton scattering. They look similar on the surface. In all three cases, an observer measures a photon with a lower frequency and lower energy than the frequency and energy at the point of emission. In all three cases, the photon travels at the speed of light before, during, and after the process. But the physics behind each one is completely different. Doppler redshift is an observer effect. The photon hasn't changed at all. Different observers in different states of motion assign different frequencies to the same photon. No energy has been transferred, deposited, or created. The apparent energy change is a consequence of relative motion. Gravitational redshift arises from the geometry of spacetime. A photon emitted deep in a gravitational well is measured with a lower frequency by an observer higher up. Because clocks tick at different rates at different gravitational potentials, the photon itself has not been acted on by a force in the classical sense. No energy has been mechanically extracted from it. The shift is a consequence of how time flows differently in curved spacetime. Compton scattering is a genuine physical interaction. The photon collides with an electron, transfers energy and momentum, and emerges with a lower frequency. Energy has gone somewhere specific, into the kinetic energy of the electron. The books balance. Conservation of energy holds in the straightforward, familiar way. These three mechanisms are not interchangeable. They are not different descriptions of the same thing. They are fundamentally different physical processes that all happen to produce the same observable result, a photon with a lower frequency than it started with. Understanding the difference between them is crucial for understanding how the universe works. Because when an astronomer observes a redshifted photon from a distant galaxy, the explanation for that redshift matters enormously. Is the galaxy moving away from us through space, producing a Doppler shift? Is the photon climbing out of a deep gravitational well, producing a gravitational redshift? Did the photon scatter off matter along the way, losing energy through Compton scattering? Each explanation implies different things about the source, the intervening space, and the structure of the universe, and there is a fourth mechanism we haven't discussed yet, one that is perhaps the most profound of all, one that doesn't fit neatly into any of these three categories, one that involves the universe itself stretching the photon as it travels across billions of light years of expanding space. This is cosmological redshift, and it raises questions about energy and conservation that push physics to its very limits. But before we go there, hold on to what you've learned so far. There are multiple distinct reasons why a photon can be measured with less energy than it started with. Some of those reasons involve genuine energy transfer. Some involve differences in perspective between observers. Some involve the structure of space-time itself. And in every single case, without exception, the photon's speed through vacuum remains unchanged. 300,000 kilometers per second. Always. No matter what happened to its energy, no matter what process shifted its frequency, the speed of light is constant. It is the one quantity that nothing in the universe can alter. Not motion, not gravity, not collision, not the expansion of space itself. We've now seen three distinct ways that a photon can be measured with less energy than it started with. The Doppler effect, where relative motion between source and observer shifts the frequency. Gravitational redshift, where the curvature of space-time and the different rates at which clocks tick at different gravitational potentials change the frequency an observer records. And Compton scattering, where a genuine physical collision transfers energy from the photon to an electron. Each mechanism is different. Each has different physics behind it. But each one confirms the same remarkable fact. The photon's speed through vacuum does not change. Only the frequency changes. Only the energy changes. The speed remains locked at 300,000 kilometers per second. But there is a fourth mechanism. And in many ways, it is the most profound, the most unsettling, and the most difficult to fully understand. Because this one doesn't involve the motion of the source or the observer. It doesn't involve gravity bending space-time around a massive object. It doesn't involve a collision with matter. This one involves the universe itself, the expansion of space, the stretching of the very fabric through which the photon travels. This is cosmological redshift, and it forces us to confront questions about energy that push physics to its absolute limits. Here is the basic picture. The universe is expanding, not in the sense that galaxies are flying outward through space like shrapnel from an explosion. That is a common misconception. What is actually happening is that space itself is stretching. The distance between galaxies is increasing because there is literally more space between them with each passing moment. Space is being created, or more precisely, the metric of space-time is changing, so that distances between objects that are not bound together by gravity or other forces grow larger over time. This expansion was first observationally confirmed in 1929 by Edwin Hubble, who showed that distant galaxies are receding from us, and that the speed of recession is proportional to distance. But the theoretical framework had been developed even earlier. In the late 1920s, the Belgian physicist Georges Lemaître used Einstein's general relativity to show that the universe could not be static. It had to be either expanding or contracting. Einstein himself had initially resisted this conclusion, adding a fudge factor to his equations called the cosmological constant to keep the universe from expanding. He later called this his greatest blunder when Hubble's observations confirmed that expansion was real. Now, here is what expansion does to light. Imagine a photon emitted by a distant galaxy billions of years ago. That photon heads toward us, traveling at the speed of light through the vacuum of space. But during the billions of years it takes for that photon to cross the distance between us and the galaxy, space itself is expanding. The photon is traveling through a medium that is stretching while the photon moves through it. And as space stretches, the photon's wavelength stretches with it. Think of it this way. Imagine drawing a wave on a rubber band. The wave has peaks and troughs and a specific wavelength. Now stretch the rubber band. As the rubber stretches, the distance between the peaks of the wave increases. The wavelength gets longer. The wave hasn't been pushed or pulled by any force. Nothing has interacted with it. The medium it is drawn has simply expanded, and the wave expanded along with it. This is essentially what happens to a photon traveling through expanding space. As the universe expands, the photon's wavelength stretches. Longer wavelength means lower frequency. Lower frequency means less energy, because E equals h times f. By the time the photon reaches our telescopes, after a journey of billions of years, its wavelength may have doubled, tripled, or stretched by a factor of 10 or more. The photon that started as ultraviolet light may arrive as visible red light, or even as infrared radiation. The photon that started as visible light may arrive as a microwave. This is cosmological redshift, and it is the dominant reason why light from very distant galaxies is so dramatically redshifted. The further away a galaxy is, the longer its light has been traveling, and the more the universe has expanded during that journey. So the more its light has been stretched. This is why Hubble found that redshift is proportional to distance. It isn't because more distant galaxies are moving faster through space. It is because their light has traveled through more expanding space. And here is where things get genuinely difficult. Because with every other type of redshift we've discussed, there was a clear answer to the question, where did the energy go? With Doppler redshift, the energy didn't go anywhere. It was an observer effect. Different observers measured different energies for the same photon. There was no missing energy to account for. With Compton scattering, the energy went into the electron. You could measure it, track it, confirm conservation. Even with gravitational redshift, although the explanation is subtle, you can understand the frequency shift in terms of time dilation between two locations. And within the framework of general relativity, energy can be consistently defined locally. But with cosmological redshift, the question of where the energy went is far more complicated. The photon genuinely has less energy when it arrives than when it was emitted, and there is no particle that absorbed the difference. There is no electron carrying away the missing energy. There is no object you can point to and say, the energy went there. The photon just has less energy now because the universe expanded while it was in transit. So where did the energy go? This is one of the deepest and most honest questions in all of physics. And the honest answer is that the question might not have a clear answer. Not because physicists are being evasive, but because the concept of global energy conservation, the idea that the total energy of the universe is a fixed number that never changes, does not straightforwardly apply in general relativity when the universe itself is expanding. In ordinary physics, energy conservation is rock solid. In a closed laboratory, energy is never created or destroyed. It changes form, from kinetic to thermal, from chemical to electrical, from radiation to matter, but the total always adds up. This is one of the most tested and confirmed principles in all of science. But the universe is not a closed laboratory in the usual sense. General relativity describes a spacetime that is dynamic, that changes shape, that expands or contracts. And in a dynamic spacetime, the usual definition of total energy becomes problematic. The mathematical tools that guarantee energy conservation in ordinary physics, tools related to something called Noether's theorem, rely on the laws of physics being the same at every moment in time. This property is called time translation symmetry. If the laws of physics today are the same as the laws of physics tomorrow, then energy is conserved. But in an expanding universe, this symmetry is broken. Not because the laws of physics are changing. The equations of general relativity are the same at every moment, but the space-time itself is changing. The metric, the mathematical object that describes distances and durations in space-time, is evolving with time. And when the metric changes, the usual prescription for defining a conserved total energy does not work. You can define energy locally. You can track energy in small regions. You can confirm that energy is conserved in any local experiment you can perform. But when you try to add up all the energy in the entire expanding universe and ask whether the total is constant, the question itself becomes ambiguous. Different ways of defining total energy give different answers, and none of them is obviously more correct than the others. This does not mean physics is broken. It does not mean energy conservation is wrong. It means that the concept of total energy in the universe is more subtle than we might naively expect. Energy conservation, as we know it from everyday experience, is a consequence of how physics works in small, flat regions of space-time. Laboratories, solar systems, even galaxies. In these contexts, space-time is approximately flat, time translation symmetry approximately holds, and energy is approximately conserved in the usual sense. But when you zoom out to the scale of the observable universe, where the expansion of space is significant, the familiar notion of energy conservation requires more careful treatment. Some physicists argue that the energy lost by cosmologically redshifted photons simply disappears. It is not transferred to anything. It is not stored anywhere. The total energy of the universe, if such a thing can be meaningfully defined, is not constant. Others argue that the energy is accounted for by the gravitational field itself, that there is a kind of gravitational potential energy associated with the expansion that balances the loss. And still others argue that the question is meaningless, that total energy in an expanding universe is simply not a well-defined quantity, and asking where the energy went is like asking what is north of the North Pole. It's a grammatically correct question that doesn't actually have an answer. Let me try to make this more concrete because it matters. In your kitchen, energy conservation is straightforward. You boil water on a stove. The gas flame releases chemical energy. That energy heats the pot. The pot heats the water. Some energy escapes as heat into the room. But if you carefully measured every joule, the input from the gas flame would exactly equal the sum of the energy in the hot water, plus the energy lost to the surrounding air. Nothing is missing. The ledger balances perfectly. This works because your kitchen is a small, flat region of space-time where the rules of energy conservation apply cleanly and without ambiguity. Now, imagine trying to do the same accounting for the entire universe. A photon is emitted by a galaxy 10 billion years ago. It travels through expanding space for 10 billion years. It arrives at your telescope with less energy. You look at the photon, you look at the galaxy, you look at the space in between, you try to find the missing energy, and you realize that the space in between is not the same space it was when the photon started its journey. There is more of it now. The stage itself has changed. The container has expanded. It is as if you were trying to balance the books for a bank vault, but the vault kept getting bigger while you were counting, and the rules of accounting were written for a vault that stays the same size. The old rules still work perfectly inside any small room of the vault, but for the vault as a whole, the total doesn't quite add up the way you expect, and it is not obvious whether that means something is wrong or whether it means you need a new way of keeping score. The important thing for our purposes is this: cosmological redshift is real. It is measured every day by astronomers around the world. Photons from distant galaxies arrive with lower frequencies and lower energies than they were emitted with. And there is no simple, universally agreed upon answer to where that energy went. This is not a failure of physics. It is a frontier of physics, a place where our understanding is still deepening, where the questions are harder than they first appear, and where the answers require a level of subtlety that goes beyond the familiar energy conservation of everyday experience. And through all of this, the speed of those cosmologically redshifted photons is exactly 300,000 kilometers per second. They arrive at our telescopes at the same speed as every other photon in the universe. Their energy has changed. Their frequency has changed. Their wavelength has changed. Their speed has not. The most dramatic example of cosmological redshift is not some faint galaxy at the edge of the observable universe. It's the cosmic microwave background, the faint hiss of radiation that fills every cubic centimeter of space in every direction you look. This radiation is the oldest light in the universe. It was emitted roughly 380,000 years after the Big Bang, at a moment when the universe had cooled just enough for atoms to form for the first time. Before that moment, the universe was a dense, opaque fog of free electrons and protons. Photons couldn't travel more than a short distance without colliding with an electron. The universe was essentially glowing white-hot in every direction, like the inside of a furnace. Then, almost suddenly, the electrons and protons combined to form neutral hydrogen atoms. The fog cleared. the universe became transparent. And all those photons, all that light from the primordial furnace, were released to travel freely through space for the first time. When those photons were released, the universe had a temperature of roughly 3,000 Kelvin. The radiation peaked in the near-infrared, but radiated strongly into the visible range as well. As if you had been there, and you obviously could not have been, the sky in every direction would have glowed a deep orange-red, like the surface of a cooling star. That was the color of the universe at 380,000 years old. Those photons have been traveling ever since. For 13.8 billion years, they have been crossing space. And during all that time, the universe has been expanding. The wavelengths of those photons have been stretched by a factor of roughly 1,100. Light that was once a deep orange glow has been stretched into microwaves. The temperature of that radiation, as measured today, is about 2.7 Kelvin. That is 2.7 degrees above absolute zero. The primordial furnace has been redshifted into a faint, cold whisper that you can detect with a radio antenna but never see with your eyes. Every single one of those CMB photons is still traveling at 300,000 kilometers per second. They have been traveling at that speed for 13.8 billion years. Their energy has dropped by a factor of roughly 1,100. And their speed has not changed by a single meter per second. The cosmic microwave background is the universe's longest running demonstration that energy loss does not mean slowing down. Now, I want to address a specific idea that comes up almost every time cosmological redshift is discussed. It is called the tired light hypothesis, and it is wrong. But it is wrong in an instructive way, so it is worth understanding what it claims and why it fails. The tired light hypothesis was proposed in 1929 by the Swiss astronomer Fritz Zwicky. The idea is simple and intuitive. When light travels a long distance through space, maybe it gradually loses energy along the way. Maybe space itself, or something in it, is slowly sapping energy from photons as they travel. Like a traveler getting tired on a long journey, the photon arrives exhausted, with less energy than it started with. This would explain why distant galaxies are redshifted without needing an expanding universe. The redshift would simply be a consequence of distance. The further the light has traveled, the more energy it has lost, and the more redshifted it appears. This is an appealing idea because it avoids the conceptual difficulty of an expanding universe. You don't need to explain how space can stretch or what that even means. You just need a mechanism that drains energy from photons over long distances. Simple, elegant, and wrong. The tired light hypothesis fails for several reasons. First, and most decisively, it predicts that distant objects should appear blurry. If photons are losing energy through some kind of scattering or interaction with the medium of space, they should also be deflected slightly, changing direction by small random amounts. Over billions of light years, these small deflections would add up, smearing out the images of distant galaxies. But we observe distant galaxies with sharp, clear images, even galaxies billions of light years away. The James Webb Space Telescope has captured stunningly detailed images of galaxies that emitted their light more than 13 billion years ago. Those images are crisp and well-defined. There is no blurring. This rules out any mechanism that involves the photon interacting with some medium along its path. Second, tired light predicts the wrong relationship between redshift and the dimming of distant objects. In an expanding universe, distant supernovae are not only redshifted, but also appear to evolve more slowly, as if they were being played in slow motion. This effect, called time dilation of distant events, is a direct prediction of the expanding universe model. Light curves of distant supernovae, graphs showing how their brightness changes over time, are stretched by exactly the factor predicted by the expansion model. Tired light predicts no such time dilation. The light would arrive redshifted, but the supernova would not appear to be in slow motion. Observations match the expanding universe prediction and contradict tired light. Third, tired light cannot explain the cosmic microwave background, the faint radiation that fills all of space, left over from the early universe. The CMB has a nearly perfect thermal spectrum, exactly matching the radiation that would be emitted by a hot, dense universe that has been cooling and expanding for 13.8 billion years. Tired light provides no explanation for this radiation. It cannot produce a thermal spectrum with such precise characteristics. The CMB was first detected in 1965 by Arno Penzias and Robert Wilson, and it has since been measured with extraordinary precision by multiple satellite missions. Its existence is one of the strongest pieces of evidence for the Big Bang and the expanding universe, and it is completely incompatible with tired light. So the idea that photons simply get tired during their journey through space is ruled out by observation. A photon does not lose energy merely because it has traveled a long distance through empty, static space. If the universe were not expanding, a photon traveling through perfect vacuum would maintain its frequency and energy indefinitely, no matter how far it traveled. There is no friction in vacuum. There is no resistance. There is nothing to drain energy from a photon moving through empty space. The vacuum does not slow light down. It does not tire light out. It does not sap its strength. A photon in vacuum will travel forever, at the same frequency, the same energy, the same speed, unless something specific acts on it. Expansion of space, gravity, a physical interaction with matter. Without one of these, the photon persists unchanged. Now, before we close, there is one more distinction that needs to be made. Because when people hear that nothing can slow light down, they sometimes object. What about glass? What about water? What about diamond? Light travels slower through glass than through vacuum. Everyone knows this. That is why a prism splits white light into a rainbow, because different colors of light travel at slightly different speeds through glass, bending at slightly different angles. So isn't light slowing down in those materials? Yes. Light does travel more slowly through transparent materials than through vacuum. In glass, the effective speed of light is roughly 200,000 kilometers per second, about 2/3 of its vacuum speed. In water, it is about 225,000 kilometers per second. In diamond, it is only about 124,000 kilometers per second, less than half its vacuum speed. But this is a completely different phenomenon from what we have been discussing. What happens inside a material is not that the individual photons slow down. What happens is that the photons interact with the atoms and electrons of the material. A photon enters the glass and is absorbed by an atom. A tiny fraction of a moment later, the atom re-emits a photon. That photon travels at the speed of light through the space between atoms, then gets absorbed by the next atom and re-emitted again. This process of absorption and re-emission repeats countless times as the light passes through the material. Each individual photon in the tiny gaps between atoms is traveling at the full speed of light. but the overall progress of the light through the material is slowed by all those pauses, all those absorption and re-emission events. The effective speed, the average speed of the light wave as it works its way through the material, is less than the vacuum speed of light. But no individual photon is traveling slower than 300,000 kilometers per second through the vacuum between atoms. This is the crucial distinction. When we say the speed of light is constant, we mean its speed in vacuum, its local speed through empty space. That speed is 300,000 kilometers per second, always, everywhere, under all circumstances. The reduced speed of light in a material is an emergent property of the interaction between photons and matter, not a change in the fundamental speed of the photon itself. And this brings us at last to the answer to the question we started with. How does light lose energy without slowing down? The answer is that energy and speed are simply not connected for light in the way they are connected for everything else you've ever encountered. For a ball, a bullet, a car, a planet, energy and speed are locked together through mass. The kinetic energy formula, 1/2 mv squared, chains them inextricably. If the energy changes and the mass stays constant, the speed must change. There's no other option. The mathematics demands it. The physics enforces it. Every experiment confirms it. But a photon has no mass. Zero. It is not described by the kinetic energy formula. It is described by Planck's relation. E equals h times f. Energy equals Planck's constant times frequency. Speed does not appear in this equation. It is not a variable. It is not a factor. The energy of a photon is determined entirely, completely, exclusively by its frequency. How many times per second the electromagnetic wave oscillates. That is it. Nothing else. When a photon loses energy, its frequency decreases. Its wavelength gets longer. It shifts toward the red end of the spectrum. But its speed does not change. It cannot change. A photon must travel at the speed of light. It is a requirement imposed by the structure of space-time itself, by the fact that photons are massless. A massless particle has no option. It cannot travel slower than light. It cannot travel faster. It moves at exactly 300,000 kilometers per second through vacuum, and nothing in the universe can alter this. Not the motion of the source, not the motion of the observer, not the curvature of space-time around a black hole, not the expansion of the universe, not a collision with an electron, nothing. A photon begins its existence with a particular frequency and a particular energy, determined by whatever process created it. A nuclear reaction in the core of a star. An electron jumping between energy levels in an atom. A particle annihilating with its antiparticle. Whatever the source, the photon is born with a frequency, and that frequency sets its energy. Then the photon travels, and during that journey, things can change the frequency an observer eventually measures. Relative motion between the source and observer compresses or stretches the waves, changing the frequency through the Doppler effect. Differences in gravitational potential change the frequency through gravitational redshift. Because clocks tick at different rates in different parts of a gravitational field, the expansion of the universe stretches the photon's wavelength during its journey through cosmological redshift. Physical collisions with matter transfer energy from the photon to electrons through Compton scattering. Each of these processes changes the photon's frequency. Each one changes the energy an observer measures. And none of them, not a single one, changes the photon's speed through vacuum. The speed of light is not a consequence of how much energy the photon carries. It is a consequence of the photon being massless and of the structure of spacetime itself. Energy and speed are completely, fundamentally, irrevocably decoupled for light. This is what makes the photon one of the most extraordinary objects in the universe. It carries energy without mass. It moves without being able to stop. It can traverse the entire observable universe, crossing billions of light years, and arrive at its destination with a fraction of the energy it started with, having been stretched and shifted and scattered along the way, and it arrives at exactly the same speed it left with. Not approximately the same speed, exactly the same speed, to the last decimal place. Unchanged, unchangeable. Everything you know from everyday life told you that losing energy means slowing down. And for everything with mass, that is true. But light is not everything. Light is something else entirely. Something that carries the information of the universe across the void, that reveals the motion of galaxies, the curvature of space-time, the expansion of the cosmos itself, all through the simple, quiet fact of its changing color. Not through any change in its speed. Its speed is the one thing the universe will not let it change. So the next time you see starlight, understand what you are really seeing. Those photons may have traveled for years, centuries, or billions of years to reach your eyes. They may have been stretched by the expansion of space, bent by the gravity of galaxies, scattered by clouds of electrons. They may carry a fraction of the energy they started with. They may have shifted from blue to red, from visible to infrared, from high energy to low. But they arrived at your eye at exactly 300,000 kilometers per second. The same speed they have always traveled. The same speed they always will. Light doesn't lose energy by slowing down. It loses energy by changing its frequency, by shifting its color, by altering the rhythm of its oscillation. And it does all of this while racing through the vacuum at the fastest speed the universe allows. Unchanged in velocity, unstoppable in motion, carrying less energy, but carrying it at the same relentless, absolute, unwavering speed. That is how light loses energy without slowing down, and that single fact tells you something deep about the universe you live in. Energy and speed are not the same thing, not for light. And light, the fastest, most fundamental messenger in the cosmos, has been telling us this since the beginning of time. We just had to learn how to listen. And perhaps that is the deepest lesson of all. We arrived at this question tonight carrying an assumption so fundamental, so deeply embedded in our experience, that we didn't even recognize it as an assumption. We assumed that energy and speed must be connected, that losing one means losing the other. We assumed this because every object we've ever held, every ball we've ever thrown, every car we've ever driven confirmed it. That assumption served us well. It is correct for everything with mass. It is one of the most reliable pieces of intuition the physical world has ever given us. But the universe is under no obligation to match our intuitions. And when we examine light carefully, when we looked at the actual equations and the actual experiments and the actual observations, we found that our assumption was wrong. Not a little wrong. Completely wrong. Energy and speed are locked together for object with mass. They are completely independent of objects without mass. Two entirely different relationships. Two entirely different sets of rules. Both true. Both operate side by side in the same universe, governing different kinds of things. The ball on your floor obeys one set of rules. The photon crossing the cosmos obeys another. And both sets of rules are consistent, beautiful, and confirmed by over a century of precision experiments. The universe is not contradicting itself. It is simply richer than we expected, deeper than we assumed, more varied in its principles than our everyday experience prepared us for. Light does not slow down when it loses energy. It changes color. It shifts its frequency. It alters the rhythm of its oscillation. And it does this while racing through the darkness at the one speed the universe holds sacred. The speed at which nothing can change. The speed of light